Welcome friends once again to my NPTEL MOOC module on exploring healthcare survey data. We are on the very last but 1 week of the module. We have been discussing about healthcare data, and on this particular lecture we are trying to understand generalized linear model. This is, as you know, that when your linear model has certain limitations where all the assumptions are not fulfilled, we go for some generalizations of that linear model. Now, I am just going to discuss about who has developed, how it has emerged. GLM is an advanced statistical modeling technique that generalizes the linear model. It was developed by John Naylor and Robert Wedderburn in 1972. It is an umbrella term that encompasses many other models, which allows the response variable, that is y, to have an error distribution other than a normal distribution. Linear regression model is not suitable if the relations between x and y is not linear. For example, x increases exponentially. If it is there, likewise our exponential distribution like cumulative density function, which is not linear in fact, in that case linear regression is not suitable. Similarly, another one is called variance of error in the y, that is not constant and varies with x. So, the variance, if it is not constant throughout, as we already know that linear regression model is not fitted. In that case, we go for some forms of transformation. Response variable is if it is discrete or categorical rather than a continuous one, in that case linear is also not applied. Therefore, we will think of some possibility of some generalization or generalized least square method or generalized least square model or generalized linear model. GLM extends linear model by allowing each outcome of the dependent variable to come from a large range of probability distribution, namely the normal distribution, the Poisson distribution, the binomial distribution and the gamma distribution. You might have heard about these distribution. It has certain specifications, certain features. Poisson, we know that it has certain count data. Binomial, we know that it follows Bernoulli distribution with binary numbers. Okay. So, gamma functions are accordingly defined. Normal distribution where the data is of bell shape kind. Symmetry is usually identified. The generalized linear models were born out of a desire to bring under one umbrella a wide variety of regression models that span the spectrum from classical linear regression models for real value data to models for counts based data such as logit or probit or Poisson, to models for survival analysis, etc. Just to give another example to Poisson is that if you have certain count data such as number of consultations of doctors, number of visits to the doctors, those are simply count, not by its continuous series. The number of consultation cannot be just 1.8, 1.9 or 1.2, there is no fraction possible, it has to be a count or absolute number. Okay. Therefore, they are called Poisson kind of data. So, GLM is made of a linear predictor, of course, that is mentioned as with a function called beta naught plus beta 1 x 1 I plus 2 beta p x I p I, and two functions are usually discussed in the case of GLM setup. One is called a link function, which describes how the mean or the expected mean is equated with the population mean, depends on the linear predictor, that is the predictor value of the mean. And second one is the variance function that describes how the variance, that is the var of yi, depends on the mean value of it. So, and then that can be of this value as per the equation, where the dispersion parameter theta is considered to be constant. Okay. Some of the components those are usually discussed in GLM are called random component, systematic component and link function. Random component is something that refers to the probability distribution of the dependent variable. For example, normal distribution for y in the linear regression or binomial distribution for y in the binary logistic function. In case of systematic component, it specifies the explanatory variable such as x1 to xk variables in the model as a combination of linear predictors. Link function specifies the link between random and systematic components. It says how the expected value of the response relates to the linear predictor of explanatory variables. Okay. And these are given in this equation with the function expected value of y, how the function further transformation of that function is also related to the expected value of y for linear regression, and that can be also applied through the logit function of the pi that is discussed. Accordingly, we said it as logistic regression. Here is a summary of GLM following Agresti paper of chapter 4 2013. It has given the GLM functions or models how it is applied. As we know, the linear regression is applied when the data is continuous, but an ANOVA or ANCOVA analysis of covariance or variance are also discussed in the context of categorical and mixed data. The link function gives the identity of it, identity of the variable that is discussed. The randomness is in fact defined to be normal. Okay, the distribution is defined to be normal. So, whereas in case of the specific GLM model like logistic, log linear, Poisson and multinomial response, the random number table or randomness of this distribution is no more normal. They are either binomial, Poisson or multinomial, and according the link function is defined as logit log function or generalized logit function, and therefore, it has mixed responses. Okay. So, the linear model as compared to GLM is mentioned here. In linear regression model, the dependent variable y is expressed as a linear function of all the predictors. The underlying relationship between the response and the predictors is linear. Also, the error distribution should be normally distributed. Coming to the context of GLM, this allows us to build a linear relationship in fact between response and predictors, even though their underlying relationship is not linear, but still it actually emerged with the linear relationship with certain transformation. This is made possible by using the link function, the way we have discussed in the previous slide, which links the response variable to a linear model. Unlike linear regression model, the error distribution of the response variable need not necessarily to be defined as normally distributed. The errors in the response variables are assumed to follow an exponential family of distribution. Therefore, we say that though distribution are accordingly defined maybe of binomial, Poisson or gamma, but that has to be that those are part of the exponential family of distribution. There are certain assumptions of GLM. The first one is that the data should be independent and random. The response variable does not need to be normally distributed. The response variable, that is yi, need not be normally distributed, but the distribution is from an exponential family, not from a normally distributed family. Okay. So, binomial, Poisson or multinomial or maybe normal, but that should still follow a exponential family. The original response variable need not have a linear relationship with the independent variables, but the transform response variable through the link function is linearly dependent on the independent variables that we have just discussed. Another assumption is that the homoscedasticity need not be also satisfied, since our distribution is following a different exponential format. So, it is need not required to be satisfied. So, errors are independent, but need not be normally distributed. feature engineering on the independent variable can be applied. That is, instead of taking the original raw independent variables, variable transformation can be done, and the transport independent variables such as taking a log transformation, squaring the variables like reciprocal of the variables can also be used to build the GLM model. So, there are various forms of transformation we do to develop a GLM model. Then various generalized least square methods are like linear regression for continuous outcome with normal distribution. In that case, identity link function is used, which is the simplest link function, and the response is continuous. Predictors can be continuous or categorical or can be transformed. Errors are distributed normally and variance is constant in case of linear regression. But in case of binary logistic regression for continuous dichotomous or binary outcomes with binomial distribution, these are another type of generalized least square method. Poisson regression for count based outcomes with Poisson distribution. Here that counts are expressed as a linear combination of the explanatory variables. So, the link function that is used here is usually called the log link function. Okay. We follow the command that is a GLM that feeds generalized least square models of y with covariates of x. So, the further g is taken as the transformation of the expected value of y, that should follow a normal distribution with x beta. Okay. And y follows the f density function, f stands for the density function. G is called the link function because of some transformation, and f is the distribution family, or usually we present it the CDF type of functions. Substituting various definitions for G function and f results in a surprising array of models. So, that is if y is distributed as Gaussian normal or G is the identity function, we have the expected y is nothing but the normal distribution or normal or linear regression. If G is a function of the variables with the transformation called G as the logit function, if any y is distributed as Bernoulli kind, we have the logit distribution, that is otherwise called Bernoulli or logistic regression, that follows a sigmoid kind of function where the concentration are usually at the extreme ends. Okay. So, if G function is the natural log function, in that case usually we go for the Poisson kind of distribution. So, Poisson distribution are for the count data. So, log ln natural log and expected value will convert the data to a linear function. Okay. Therefore, it is called log linear functions. So, what now we are just comparing between transformation and GLM. In some situations, a response variable can be transformed to improve linearity and homogeneity of variance, so that a general linear model can be applied. This approach has some flaws. Response variable has changed, transformation must simultaneously improve linearity and homogeneity of variance. Transformation may not be defined on the boundaries of the sample space that has been considered. As an example, a common remedy for the variance increasing with the mean is to apply the log transformation. If variance are there, simply take the log transformation, that will reduce the variance. Okay. So, there are other ways by which we can also do some expected value of the variance log function can also be taken. This is a linear model for the mean of y, which may not be always appropriate. If y is income, perhaps we are really interested in the mean income of population subgroups, in which case it would be better to model expected y using the GLM. GLM of this function log expected yi is actually converting to a linear function. So, some advantages over the simple linear regression which are counted and necessary to define. First one is that we do not need to transform the response y to have a normal distribution. The GLM command itself will automatically deal with this transformation. The choice of link is separate from the choice of random component, thus have more flexibility in modeling. Okay. So, the link function that we usually carry from the beginning of the command, okay, maybe like log transformation or logit at the beginning, we need to think very carefully, but in this case with simple GLM command at the end we can specify the link function and derive the result. Okay. If the link produces additive effects, then we do not need constant variance. Okay. The models are fitted via the MLE estimation, maximum likelihood estimation, thus optimal properties of the estimators are also defined. One example will also show it to you, and on the basis of that you can just think how you can able to derive the result and be confident about your result. If we fit a model based on data from a study of risk factor associated with low birth weight as suggested in Hosmer and Lemso and Sturtevant in 2013 paper, where we say that the command is equal to GLM, the first dependent variable is low birth weight and then age, then other variables with its reference categorical variable we can also mention. Now, after all such variables we can give a comma and define which family they belong to. Since we identify that that data belongs to binomial family, then your link command will be of link logit, okay, link within bracket logit, then that will be giving you the result. So, here are other way of deriving the command. Go to statistics, then GLM, generalized linear models, then generalized linear models GLM will be displayed on your screen. We will also show that to you. Okay. Stata command for GLM, there are different commands as well. I am just going to show you how you can operate just for your reference. Okay. Here is the data. Now, we wanted to operate it once. GLM is here. So, the sample data we are just operating for your reference. We have all those data. We will also open the do file simultaneously or we can directly run as per the command we have given. Okay. Here is the command. So, we simply copy and you can run for your own practice. So, here is the result on your screen. Okay. Now, this has given the idea that how the link function is defined, how families of the data is also defined. Now, this has given us the coefficients, okay, and their significance level, and on the basis of that we can take decisions of interpreting the results. So, it seems the results are similar to that of the logit function. A logit command, the way we have already specified, can also be given. Now, you mark that this is also called the coefficient, not the odd ratio. Okay. So, this has a combined operation and we need not go for logit separately. Similarly, there are other Stata commands for GLM. Once you know the link function and the family of it, when you know that your family is binomial, you can give this command. When you know your binomial family, but also you know very clearly about the function to be applied, you can give that. So, GLM with your dependent variable, independent variable should be specified. When you know that it is families of binomial type, but your distribution is more probabilistic type or distribution follows normal distribution, error term might have followed a normal distributive structure, then in that case you can apply accordingly. Similarly, other approaches are there that you can easily explore. Okay. Gamma function, if it is there, then bootstrapping through this particular command is going to be helpful for you. Another approach that you can do it through the through the window, through statistics. You can go to statistics, then it has the it has the what is called generalized linear models, then here is your GLM. Now, you can specify each of it dependent and independent variable, and with that it is possible for you, and some family name you can give it. Okay. So, with the family name, like as I already discussed, whether it is a Gaussian type, binomial, Poisson, gamma, etc., and your result will be displayed on your screen the way we have shown it to you. Okay. So, these are all I think at this moment we will come up with further details in our next episode, and with this we are going to stop here, and I look forward to your comments or queries. We will be happy to address it. Thank you.